Okay, there we go. I need to share the way I'm presenting. I apologize online. I lost internet. Let's hope that it does not happen again. Okay. Now we just wrapped up relative age. Okay, so puddle jump to technology nowadays. Can you give me a phrase specifically that we use to date things that are more modern? Things like Egyptian mummies. What do we use?
Hey, how are you doing?
Smart kid. How do we age things that are recently dead? Not like dinosaur dead, but recently dead.
The way they look.
No, numerically, like scientifically. How do we age things that still have viable tissue? Like that mammoth that was at the very, very, very end of yesterday's notes. How do we know that that thing was at the very tail end of the Ice Age? Nobody will talk about it. Oh. We use what are called radioisotopes. And so we didn't understand this stuff until the latter part of the 1800s, almost the 1900s. We just didn't have the technology to be able to do it. We didn't understand electricity, essentially, is what it comes down to. If you have viable tissue, so what we think of as a mummy, whether it be Egyptian or Aztec or the bog mummies we talked about yesterday, there's actual tissue that we can run through one of these machines, which is about the size of this desk. These mass spectrometers, and we can determine how much of a specific radioisotope, in this case, would be carbon-14. How much is left? And knowing how much is left, we can sort of like proactively is the right phrase. We can go backwards and figure out with how much is left, how many half-lives have occurred. I honestly do not know if I gave you multiple attempts on today's assignment. I need to go into that and double check it. Give me just a second. All right, so absolute age dating. We're going to get finite numbers now. I know with the last couple of slides that were put onto your Canvas yesterday, they actually put years down on the side. We didn't know that. We didn't know any of that until we had the ability to actually do radioisotope dating. We go way back. So pre-understanding. Lord Kelvin said that the Earth couldn't be more than, give or take, 400 million years old. And now we know that's not true. It's like closer to 5 billion years old. But he said originally, before we understood anything better, that our planet, that life itself, this thing that we live on, this blue bubble that's going around our sun, was not more than 400 million years old. With the understanding with current technology, with radioactivity, we know that that's like way outside of the ballpark. Radioactivity, not all elements do this, but once you get big enough, it's like trying to put too much water inside a water balloon, and eventually it'll pop. it will break down into smaller things that are more stable. And measuring this with these mass spectrometers, these machines that are literally the size of this table, if not larger, will let us know how many half-lives have occurred. Now, each radioisotope has a different half-life. Yes, I know that was a video game from back in the I think, late 90s. It was the late 90s, it was Half-Life. Oh, I go way back to the old pencil and paper D&D days, like way back. One of those. But no, Half-Life was a computer game. One of the at the time was like a game changer, if you will, no pun intended. But yeah, Half-Life was sort of like a World of Warcraft kind of like maybe a milestone, if you will, as far as changing the game, no pun intended. And so we talked about this in the last 6 weeks. We had all these asteroids and these comets that bombarded our planet. They brought in all of these extremely heavy radioactive elements that then embedded themselves into the interior of our planet. And that's part of why our planet is still alive. These materials are still trying to break down. Some of these half-lives, like one half-life, is over 4.5 billion years old, which is approximately the age of our planet. They're still there. But the breakdown of these radioactive isotopes helps produce heat, which helps keep our planet alive. And there's one more on here. There's not. Okay, hold on, let me go back. I apologize. I didn't pull up the cheat sheet. But I mean, I don't want to say that our planet's alive like we are. We are still close. Now let's see what's this time. Absolute age. Here we go. One of my dogs got out this morning, so I got here like almost 30 minutes later than normal. My dum-dum dog. At least I got him back. He's the prettiest dog ever, but he's a dum-dum dog.
My car got out.
Cows aren't as easy to get back. Well, unless you maybe trained them with a bucket with feed. Now, that's...
Yeah, I got I bought this dog food, and they said the bag was into
When where I moved from, we had chickens, and all I had to do was say the same thing over and over, and it was like partridges, like a line of chickens that would follow me. All I had to do was call them. And all I had to do was tell them to coop up, and they would one after another. They would go inside their coop. It's weird. No, your cows, did you have them from babies?
Yeah. Well,
And they still won't listen?
No. Yeah.
That's so annoying.
Everybody gives chickens such a bad rap because they're so stupid, but if you raise them right, they really are like little puppies. Like they will listen to you. Maybe it was the
I don't think so.
well, chickens are stupid too.
Yeah.
They're chickens.
Yeah.
But all I had to do was tell them to coop up, and they would literally follow the leader into the coop. Even before it was quasi dark. Oh, I miss my hands. I do. I miss fresh yard eggs. There's nothing like a yard egg. If you've never had yard eggs, you don't understand. All right, so we're going. I am not trying to trigger anybody. We're going back to chemistry for a second, which was probably last year, if not last year, the year before. Inside an atom, and we've got 3 subatomic particles. Inside the nucleus, you've got protons and neutrons. And outside of that, like way outside of that, you've got electrons. If you took an atom and blew it up to the size of a basketball and put it on a 50-yard line inside like a professional, like, I don't know, Cowboy Stadium, the first electrons wouldn't be out until like the nosebleed seats, like way outside. That much of the atom is space. But the electrons go around the outside, your protons and your neutrons are inside. Can't change protons, you change protons, you change the element. You can change neutrons. And those make these different radioisotopes. The number of protons is a whole number, what we call a mass number. It's not those percentages that we have up there on a periodic table. Those are different, those are averages. But your radioisotopes, we didn't get this until the very end of the 1800s. And so your atomic mass number, there's a whole number, is your protons plus your neutrons. Now, I've got to cheat and look at my whole periodic table here, because I can't see that one from over here. After radon, no, that's not a true statement. After Lutetium and Lawrencium, a lot of them are in parentheses on the periodic table, and most of those do not exist in a normal state on this planet. At least if they do, it's not for long. But isotopes have different numbers of neutrons. It's still the same element. Well, they decay differently. In fact, carbon, which is what most of us are made up of. In fact, you could, I don't know if I mentioned this yesterday or not, you could cremate somebody and literally send off the cremated remains and turn them into diamonds. People have done it. It's really morbid and messed up, okay? But you can send off somebody's cremated remains, which are carbon, and then what they do is inside a lab environment, they pressurize it, temperature and pressure, and they literally turn them into a synthetic diamond. It's a real diamond. It's just a lab-made diamond, which then you could wear, which is really weird. You want to be a diamond?
Yes.
You can do it. You can do it. You can do it.
What's it called?
I think I'd rather be a tree.
You'd rather be a tree. Well, you can do that too nowadays. Nobody knows when they're going to die, but let's say that you put it into your will that you want to be essentially turned into a tree. It's almost like your body is put into a burlap sack, if you will, and then whatever kind of tree you want, maple, oak, I don't know, whatever. Literally, your remains will nutrient, whatever the right phrase I'm looking for, will feed said tree.
That's kind of cool.
I'm not joking, it actually exists.
You'd be the one who you let pine cones in.
Oh, those sweet gums, the round ones that you step on them and no. I don't know if you guys have sweet gums here. They're horrible. It's almost like Virginia buttonweed, but like big. Oh, they're nasty. They're nasty. There's nothing like stepping on one of those and you're not paying attention. So, isotopes have a different mass. Okay, they're still the same element. They're still the same protons. They're still the same thing. They're still carbon. They're still uranium. They're still potassium. They're still rubidium. But these different numbers of neutrons are going to affect the way that they decay. Now, this is, and we didn't understand this until the latter part, like almost the 1900s, the very, very latter part of the 1800s, where we can measure how much is left behind. And when we do that, we can figure out how many years have passed. You have to know the half-life. Like I said, we didn't understand any of this stuff until really electricity. So we can thank Tesla and Edison fighting each other. And poor Tesla. Poor Nikola Tesla. Edison was literally the Wizard of Menlo. He was a thief. He invented the patent. And then he proceeded to patent everybody else's idea. He did not invent the light bulb. He did not invent the electric chair. He did not invent any of that crap. He patented it. He tweaked it and then said, "This is mine." That is what Edison did. I'm not like, he also electrocuted an elephant in public, dogs in public, people in public. You can even find poor Topsy, the elephant, being electrocuted in public. There is no sound. It is grainy. It is black and white. It is from the late 1800s. But yeah, you can still find it. All different kinds of messed up stuff. Trying to remember if there's another page. There's not. So knowing a half-life and knowing how much of an isotope is remaining within a sample, mathematically we can calculate how old said thing is. So those trilobites, in fact, the ones that I was passing around the other day, or maybe 2 days ago, those weren't the original samples. Those were casts. They were replicas of the originals. But the original sample, if you just took a teeny tiny little sliver off, ran it through a mass spectrometer, and you dated it specifically with a isotope of uranium that has a half-life of 4.5 billion years. However much is remaining will let us go backwards, if you will. And I'm not going to make you guys do logarithms in line. But however much is remaining will let us know specifically how old said organism is. And there are different isotopes that we use. We'll get more into that tomorrow. Radioactive decay. There are 3 types, specifically alpha, beta, and gamma. Alpha is nothing but a helium nucleus. That's all it is. Beta is an electron. Gamma is pure energy. Now, we're not going to go into gamma radiation with this. We're not. But alpha, you've got 2 protons and 2 neutrons. Helium's atomic number's 2. 2 protons, 2 neutrons. When that's emitted, it causes essentially a chain of events. This is how our nuclear power plants work. You've got this nucleus that's spat out, and it hits other things, which then causes the next sequence to occur, gives off massive amount of energy, causes heat. I have no idea what it is. There it is. And then we collect that, turn it into energy. Let's see. Let me freeze this and check on Let's see here. Let me check on one before I forget. Uh-oh, I see a, do you become one diamond or multiple? That's a good question. Depending on how much of a carbon residue is left behind. This is very morbid, but I can speak of this from a personal level. When my husband passed away, I had him cremated, and he's literally, this is very messed up. He is literally in 3 different boxes in my closet because I haven't figured out what to do with the remains yet. So, Joseph online asked, do you become one diamond or multiples? Now, how much carbon residue is necessary to produce a diamond, and of which how large, that I do not know. I don't know the answer to that. But I have three cremated, like they're about yay big, like size of a brick, if you will. 3 of them from him. We just haven't figured out what to do with them yet. It was not expected for him to pass away at 42 years of age. Let's see here. Let me find the box.
It's $3,000.
It's expensive. Are you looking it up right now? How to do that? I mean, you can do it. It is a thing, and people do it. Okay, I see Taylor. I see Braylon. Sorry, I'm trying to go back and do attendance while we're doing this. Now, as far as color and whatnot, that I don't know. I just know that it is possible.
If you want to do a red diamond, maybe 25,000.
I mean, it's honestly, I mean, if you're dead, you're dead. It's not like you're going to know what's happening with your remains, but I don't know. It's weird. It's weird, all the different things that you can choose to do with, I mean, like I said, you're dead, but proactively, I guess, like a will kind of thing, what you want to have done with said remains. Anyways, radioactive decay. Okay, so alpha is a nucleus of a helium atom to break down to neutrons. Beta is different. Beta is essentially energy. It is an electron. Either it emits an electron and it gives off essentially light. The physics teacher in me is trying to go off on a tangent, but not going to. Or it can absorb an electron. One of 2 things. If you give off an electron from a neutron, you become a proton, and your atomic number changes. If you absorb an electron, then you've also changed your atomic number. I'm not going to go into gamma radiation on this one, but you either release it, which is decay, or you absorb it, which is capture. You're either increasing or decreasing the number of protons. You have changed your element. I didn't animate any of these because this slide was way too gosh darn busy with all of the images. But rubidium 87, if it decays, I have to cheat and look at my periodic table here. So rubidium 87 is RB. Where are you at on this puppy? Just strontium, SL. I just have to find it because I do not memorize the entire periodic table. No person on the planet should memorize the entire periodic table. You've changed the atomic number. You changed the amount of protons. What is this? There we go. Here we go. So you've literally changed elements from one side to the other because you've changed the amount of protons that are available. Potassium to argon, if it goes from potassium, which is letter K, to argon, in order to go up a level, then you have changed a proton to a neutron, which means you must have captured an electron. I don't know. Here's the issue with y'all. With the whole COVID thing that happened last year, I don't know how many of you were in chemistry, but your protons are positive, your neutrons are neutral, and your electrons are negative. What changes the element is the number of protons. That is the only thing that changes the element. If you're going from potassium to argon, which is actually previous on the periodic table, then you must have absorbed an electron into a proton to change it to a neutron. Neutrons are mutations. They were not one of the first things that were created with the Big Bang. It was protons and electrons that were created with the Big Bang. A neutron is a complete and total pure mutation. But if you're absorbing electrons into a proton, you have a positive and a negative together, and they neutralize each other. You create a neutron, which is what happens in this bond. So if you're giving off an electron, then you've got a different type of decay. Uranium-238. There's all different kinds of uranium. 238 and 235 are the most common isotopes. Uranium-238 is not stable at all, and it wants to break down. The whole purpose of decay is to break down and become more stable. And when they do so, they give off massive amounts of energy in the form of heat. We collect that. It spins, it heats up the water in our nuclear power plants, causes steam, goes through pipes, spins turbines, and then we collect that and store it as energy. Uranium-238, this is specifically the one that we use to date meteorites. Its half-life is approximately 4.5 billion years. That specifically is the one that we've used to date the age of this planet. 235 is different. It's still uranium, but its half-life is only 704 million years. So those trilobites, even though those weren't originals, but those cast and molds that we passed around, those aren't aged with this guy. They're aged with something that's closer to their half-life. Don't worry, I'm not gonna make you guys do logarithms. I'm not. I'm gonna pull up the. We've got a couple other ones that I'm going to talk about specifically. Rubidium 87, the number 87 is the number of protons plus the neutrons together. That's its mass. It's way longer than the ones that we've used to date, those meteorites. Potassium 40. Ooh, I did not realize that was the last one I was. Potassium 40 is sort of like an intermittent one, but and I don't have enough time to go through every single type of radioisotope. Don't. When it comes to remains, fossils, if you will, which is what we talked about yesterday, there are certain elements that are better than others when things are like a long time dead. But if they're recently dead, like mummies, we don't use any of these. We use what's called carbon-14. But carbon-14 only goes back so much time, and then there's none left. Then we have to switch over to your heavy elements, like potassium, rubidium, uranium, plutonium, your very, very, very heavy elements. So a half-life is how much time it takes for half of said original material to go away, to change into something else. Somewhere I put my clicker and I can't find it. Oh, here it is. You have a very distinct value of a half-life. For carbon-14, it's just over, well, it's almost 6,000 years for one half-life. But like I said, even these radioisotopes, they're only good for so long, and then they're no longer valid in the case of carbon-14. Then you have to switch off to your heavier elements that last quite a bit longer. Two more. We're gonna pick up with the, like I said, I'm not gonna make you all do logarithms, I'm not. But we're going to go a little bit more in depth tomorrow with these absolute aging techniques. Depending on what we're dealing with, they could be fractions of a second, and they could be billions and billions and billions of years. So, and like I said, I'm not going to go through every single type of radioisotope. You have almost like an inverse. You have a, what do they call it? Quadratic? I'm not a math teacher. I'm not technically, but it's not a straight line. It's exponential, but inversely so. Probably, we'll just be math. Online. Yeah. I got one more slide that shows a graph, and I can't remember what I did and did not put on the Canvas page for y'all. But you have this exponential, but inversely so. At literally 50%, you've had one half-life. Okay, so you only have 50% left. If you go to a second half-life, there's only half of that left over, which is half of 50 is 25%. Half of that would be, let's see, so we got 150, 25. Half of 25 is, I swear calculators have totally messed up my math. 12.5. And you're going to keep cutting things in half again and again and again. And depending on how much of the material remains, you can go back and figure out how many half-lives have actually occurred. Give me just a second. I'm going to go through and let people know who have not done their assignments on time. Use this. This is the last. Okay, so the assignment from yesterday, which is still open, on the right button and the right class. Okay, in here, the assignment that is still open that I am missing, why does it not say, hold on. 11 for opener. I gotta drag everything to the right spot. Okay, so the assignment from yesterday, which is still open technically until 11:59. I am missing one from Sarah. I am missing one from Erica, from Kale, from Dylan. That is the one from yesterday. Some of you already done today's. You know what? I need to go back and double check and see if I'm giving you sense. Homecoming is Friday, right? It was supposed to be Disney Day today, and I have so many ears at my house from when I went to Disney 2 years ago, and I forgot to bring them. Let's see, we've got. All right, let me double check today's assignments. Yeah, it does give you 2 attempts. It does. Oh gosh darn it. Now we're going to, like I said, tomorrow, go a little bit more in depth with absolute. And then at least Monday, we'll be doing geological time scale. No, I'm so sorry. We're not getting into dinosaurs yet. Not yet. That is 4-6 weeks. The dinosaurs.